Recording. Yeah, indeed. Like this. Okay. So things that we have discussed previously is that uncertain factors in simulate that we will trying to simulate, especially that belong to discrete event simulations was basically often modeled as a statistical model. What are statistical model being used for? It being used to represent the random events, right? Random events. Therefore, um, one of the things that we need to understood here is that those random events were seen in the simulations because they don't know what kind of event it is, but they can understood that this event could match with some um, statistical distribution random variables model. Okay, so therefore we are learning about discrete random variables, which represent some random event that could appear in a discrete value. Okay, or a random event that has continuous number, so continuous random variables. So we learn about it, and then we also learn about the concept of cumulative distribution functions. Basically, it's the um, sum of the probability of these discrete random variables. Okay, and expected value. So basically, it's the mean of the value of a random variables. Okay, and the formula is represented here. So what is discrete random variables? We have explained it earlier. It's about representing variables or random events that has a finite number of possible value, like flip of a coin, which only have two, or throwing the dice, which only have six, or many other that may only have like several finite combinations of values. And the way we can represent it, the probability of those appearance of those random variables is denoted by pi, which is here, probability of, and this is representing the x representing the value of those random variables, and I is the index. So if you have index 0, so this one appearance of this value equals to 0, and the probability is some number. And remember, the sum of the number would be always equals to 1, sum of this probability, because if you have set of possible value, for example, hey, I flip a coin, the chance it is head, so coin will be head, assume we have head and the tail. The chance of it has head will be half, right? 0.5 or 50%. And the other chance, it has tail. The probability of having tails will be 50%. The sum of it will be always equal to 100%. We cannot have the sum of the probability would be more than 100. Okay. So later on, this formula or notations pi will be known as this probability mass functions. It is for discrete random variables. But for continuous random variable, it will be known or as probability density functions. Okay, so those are the terminology being used here. And this one will be known as cumulative distribution function. Okay, the sum of the probability functions. Okay, probability distribution function. Okay, next. Yeah, this is the random variables, continuous randoms. why it is called probability density functions? Yeah, because it will represent the area under the curve. Okay, the how large is this area? So if it is just a dot like this one, yeah, like this one, it will be the probability will be 0. But if you calculate the large of this area, you will have to use the integral value of it, okay, to calculate. Yeah, like this is what we learn in calculus 1 normally. So the area under this curve will be integral from this to this of this formula. So fx. Yeah, basically this one. And the same with the discrete. For continuous random variables, the the probability of things random event fallen between in this area will be represented by fx, which is yeah. Previously we have px, now we have fx. Yeah, so that's what we are discussing previously. And then, yeah, this is just an example of it. You can use those concepts to understood several things, such as if you want to know the life the life of an inspection device given by X, the probability of those device will be still live, still be able to use between 2 to 3 years will be formulated using based on their probability density functions. Okay. Yeah, this is discussed in the previous meeting. And for cumulative distribution functions, it's basically the total sum of the probability distribution functions, or for in this case, probability mass functions, up until value of x. Okay, so with that we can understood also. We are also being discussed about the expected value. The expected value is the sum of the value of the appearance multiplied by the probability of it. Okay. And then if it is continuous, it's the integral of the value multiplied by the probability density function. And we also being introduced to so-called variance. So means would represent the or expectation of x, or means of x represent the central tendency of this value. Meanwhile, the variance represents the deviation from the central tendency. Okay, so with that, you can now move on to this one. By understanding the general form of discrete random events and its probability, discrete random variables and continuous random variables, and its probability density function, as well as probability mass function for discrete random variables. Now we can see that the uh, the main applications of those statistical models were different for different system. For example, if you are going to model a queuing system, you need to understood first the characteristic of its random variables being modeled. For example, for queuing system, what are the uh, random variables normally involved? Okay. Perhaps from the previous example, you can say that for queuing system, we would have arrival times. or inter-arrival times between customer. So customer arrival. What else? The service time, perhaps. For when customer arrive and served by the server, this will be the random variables being involved. To model this in simulations, you may need to understand which kind of distribution would fit with the behavior of your customer arrival in the queuing system. Okay, and in the next slides, we will discuss about what are commonly used, what kind of a statistical model were commonly used for modeling this when modeling this. Okay, and then inventory and supply chain system. Okay, this is another area where simulation can have its role because normally things in these problems like inventory management or supply chain system will have random variables such as demand, the demands of the products being stored in the inventory or demands of the customer in the supply chains. Other than that, perhaps lead time. Okay, let's say in the inventory management system, you may have some lead time before the order that you process to replenish your inventory would be filled, right? So lead time sometimes uncertain. Yeah, most of the time actually. For example, hey, you have like I don't know. Maybe if you're working in manufacturing company of an electronic devices, let's say one of the inventory need to be stored because it's a manufacturing company. We need to have all the spare parts in our warehouse, and then one of the spare part, perhaps, let's say the battery of those electronic devices. Then you are somehow seeing that okay, to produce or to assemble our electronic devices. Next month we have thousands order. Thousands means maybe need thousands of battery. This week we only have 200 batteries. So next month, by understanding the demand, the demand is already uncertain, right? The demand uncertain, and then we need to know also if we are going to replenish our inventory. So if you want to order some more battery in order to fulfill this demand, we need to know how much of a lead time that we have. If the lead time is constant, that will be good. It will be best for the predictability of the battery that's coming. But if not, you need to understood what is the characteristics of your lead time. Okay. Yeah. So most of the time, those are the things that being modeled in the supply chain system. Okay. Another would be reliability and maintainability. This is also area which often being modeled using simulation. For example, I think it is often also in a company where they need to test a product. Yeah, for example, stress test. Let's say light bulb, for example. Uh, so for your light bulb, let's say you are going to give it warranty of I don't know, light bulb normally quite long, right? The warranty, maybe lifetime warranty. Okay, so the secret of behind lifetime warranty would be that um we need to test it. We need to like those company that able to give lifetime warranty, perhaps, I think, and you can read the theory. Normally, they will already test the lifetime of their product, the reliability, and how long it need to be maintained. Okay, maybe more to the reliability. They already test the reliability of those products can be performed well. Okay, before its failure. So this is another term, so-called time to failure. Yeah. So they test their products when, in average, and the expected value earlier, their product would be fail or not be able to use anymore. Okay. Then they compare it with the lifetime of what? Of human being, right? So if your products would be having lifetime larger than the let's say the entail of populations oh, what lifetime, so you can claim actually, hey, I can give you warranty of a lifetime, right? Because yeah, yeah, some maybe fail, like one or two, but not many because you already tested using simulations, using stress tests normally. Maintainability, also the similar case, like we need to understand the time to failures. But for the maintainability, this is called repair time or downtime. Yeah. So understanding when things will going down and then you set up their repair policy before those downtime. It's also possible. I think there is an area that's also discussed about this in the paper or in the studies that if you are interested, you can explore about it. Some other limited data. This is a very specific case study. There are often not also part of this or combinations of these models. So the key point is that different system may need different statistical models or different distributions model. Okay, so you should not choose you should not choose the distribution randomly. Hey, because I like exponential distribution, so my demand will be exponential. No, it's not work like that. So the distribution selected will be based on what? Based on the behavior of the real world variables being modeled. How do I do that? So you need to take samples that represent enough. We will also learn about how many samples were adequate. Need to take samples, and then based on these samples that adequate to represent the real world variables, you create or you calculate the goodness of fit with the distribution models that you choose. So how? Because first of all, of course, you need to each of the basic distribution model would have their characteristics, known characteristic already. And then for each of the distribution model, normally they will have parameter that can be adjusted according to the parameters in the that you can grab from the samples. Okay, then you can check the goodness of it between the real world variables that taken from the samples with the simulations distributions that you create. Okay. Okay. Now let's move on, discussing one by one of those. Queuing system. I think I mentioned earlier, two of the most important random variables in queuing system is inter-arrival times and service time. Okay. So what is inter-arrival times? Inter-arrival times is the time between one arrival of the customer to the next. Okay. And then what is service time? Service time is the time required to serve one customer or one job or one unit of demand or customer. Yeah. If the arrivals are randoms, okay, the exponential distributions are often used for the distributions. Okay, so this one, this is distributions that you can go for when the arrivals are completely random. The same with the but it's not the same with the service time. Service time relatively stable. but will have some variation. Therefore, the normal distributions is often used. Okay. And then, if the surface time cannot be negative, okay, sometimes it's like that, right? Surface times cannot be negative because yeah, it's either zero. Zero is no surface no surface time at all, but it can go through positive. So it would be truncated normal distributions will be more appropriate. Okay, and but for some variations, gamma or Weibull distributions are more general versions of exponential. Therefore, this may be sometimes more fit for the distributions of, I don't know, maybe service time, maybe inter-arrival times and stuff. Okay, in supply chain, the uncertainty comes from what? It comes from the number units of demand per order, okay, or the time between the demands, or the lead time, okay. Um, For lead time, normally gamma distributions were often being used, okay, because of its characteristics, and it would always be continuous and positive. But for demand, okay, the normally it will be a model as a Poisson distribution, Poisson distribution. And it's sometimes also negative binomials, which basically similar to Poisson, but it has longer tail than Poisson. So I don't really know how to draw Poisson distributions, but longer tail mean at the end of the distributions. So it will be have longer uh, between in those distributions graph. Um, in simulation, the distributions help also for simulating stock out risk, inventory cost, replacement timing, and service time. Okay, those are some things related to inventory and supply chain. And then for reliability and maintainability, this is a very how to say, large area of application of simulations, where normally you will simulate times to failures. Um, it to simulates like values, because it is used because of failures occurs randomly and independently over times. So therefore, exponential distributions is often being used. Uh, if but sometimes with the characteristic of standby redundancy were taken out mm, from the assumptions, you may use gamma distributions, or you can use Weibull as well to um, simulates system with a large number of defects in the system components. And sometimes you can go for normal distributions because of failures that affected by the use of the products or service. Okay. And some other areas, we can also have uniform distributions, triangular, beta, also some other distributions that also useful, Bernoulli, binomial, hyperexponentials. We will see on a glimpse all of these distributions. But again, I have no intentions to describe all of the formulations in detail. So things that you can do to best use of this, I can say, shared material is that if you are somehow having the task to simulate things, you may refer to the common distributions being used for those particular random variable first. Okay. I don't think you can need to like, hey, I need to understand Bernoulli, I need to binomial, hyperexponential for before you understand that what kind of simulations you are going to do. Okay. If your simulations were later ends up with my reference saying that I need to use Bernoulli as the variable to represent those random variables, then you can understand or read more about those Bernoulli random variables or random statistical models. Okay, random distributions, more precise. Okay, next we will talk more about the each of those distributions. First, we will cover the discrete distributions, which we mentioned earlier or as already. It is the types of the distributions where the value of the variables is finite. Okay, there are several. For example, we do have Bernoulli trials and Bernoulli distributions. We do have binomial, we do have geometrics and negative binomials and Poisson. Okay. The examples would include like which distribution would suitable for, let's say, number of customer arriving, because sometimes, hey, I know the inter-arrival times, but the number of customer arrive in each inter-arrival would also be random, so you can use that. The number of call received, the number of defect item, the number of machines that fails. These were some things that you can go for when you want to model those. Okay. Okay. So this one, the first one is the Bernoulli trials or Bernoulli experiment and so-called Bernoulli distributions. Okay. So Bernoulli trials, this something, some variables that consider like an experiment consisting of n trials. So if you click, so you experiment on n trials, n times, then you can like count from n trials that each can be an success or a failure, right? So to to how to say, to simulate those situation, you can use the Bernoulli trials distributions, where this is the general form of it. So if you have only two options, right? Either it's success or failure for each n, for each I until n. So let's say the first trial, okay, when you toss a coin, for example, you toss a coin, and then you know that what is the probability of it's going to be success, that will be P. And then what is the probability it will be failed? That will be 1 minus P. For a coin trial, it always be 1 divided by 2, right? 1 divided by 2. But for other phenomena, it may be not the case. Okay. Another, so maybe you have like for each trial, you can have maybe 0.25% will be a success, 0.75 will be failures. That's some other particular system may happen like that. So therefore, this is the general form of Bernoulli trials distributions. So the expected value or the means will be represented by this. The variance is this one. Okay. And next, we will have binomial distributions. So binomial distributions and Bernoulli is connected to one another. So in Bernoulli, we only consider what is the probability of each, right? Each trial will be success or failure. For binomials, it is used when we count the number of success in a fixed number of trial. Let's say if you have like n number of trials. So let's say you coin toss 10 times, okay? And then X will be represents what would be the probability, okay, of we have, let's say, of success of head, for example. That will be here, represented here, using this formula, okay? And for geometric distributions and negative binomial distributions is geometric distribution used to model the number of trials that required to get the first success, okay? So again, the same examples of a coin toss. What is the number of the trials for coin toss to achieve the first tail? Okay, so that you can create the probability of those using this PDF, probability distribution or probability mass function in this case. Okay, for negative binomials, it would be instead of the first success, it count the number of trials to need to get the K success. So this is a more generalized versions of the geometric distribution. Okay, next, okay, this is another important distributions that often being discussed as well. Poisson distributions is describe how many random process how can I say this? It, it used to model the number of events, okay, occurring in a fixed interval of time or space. For example, what is the number of customer arriving per hour? Okay, that is Poisson. What is the number of call received by a customer service per minute? That is Poisson distributions normally. What is the number of machine breakdowns? Okay, that is Poisson distribution as well. So the parameters of Poisson distributions, we will have this one, alpha. This alpha. Then, okay. Yeah. For example, this one. Okay, so what is the okay, a computer repaired by a person's a computer repair is beep each time there is a call for service. So a CS, customer service, is for like a repair computer repair store. So every time it will be beep when there is a call for service. The number of beep per hour is Poissonly distributed with the alpha is 2. So you need to the probability of 3 beep in the next hour. So three customer being calling. So you can put it into the Poisson distributions formula, then you will get this one. So 18% number of the probability of 3 customer will be calling in the next hour. Okay. So that would be about normal discrete random numbers and the discrete distributions. Now we talk about continuous distributions. So continuous distributions is so a random variables that can take any value but within a range of some things. Okay, so take any value in some intervals. Okay, And for that, we will have this one. We have uniform random. Okay, this is a very common one. When you have the same probability of what area probability of things happening in those particular sections, exponential distributions, and then normal distributions, Weibull distributions, and log normal. Okay. And these examples would include some things like modeling the customer service times, uncertainty rates, and then modeling the machine processing time, delivery time, repairing time, product lifetime. Those are the things that can be used from these um, continuous distributions. Okay, let's start from the one of the commonly used. Uniform distributions is distributions that assume all value between the minimum and maximums are equally likely. So it means that they have the same probability. So fx would be 1 divided by the probability of the number of the upper intervals minus the lower interval. Okay, so this is it. Then we have exponential distributions. This is what it looks like. So for exponential distribution, it's commonly used to model time between random event. Okay, so let's say the first random event is like customer arrival at time 0. The next arrivals would be what? That would be something exponentially distributed. Okay, exponential random numbers. So the parameter is this one, the lambda. The effect of this number of lambda is like this, you can see. So the larger the lambda, the lower at the beginning, but higher at the end. Okay. And then it used to model something like inter-arrival times. It used to model the exponential variables. Okay. What does it means by memoryless property? Well, it called memoryless property means that the means of probability of it is some things that used to model some things that doesn't affected by the previous event. Okay. So for example, when you have like a lamp that already worked for 2.5 hours, the chance of that it worked for 1 more hour is the same with the chance of that new lamps work for 1 hour. Okay? Because we are talking about the probability. Okay, this probability of the next event will not affected by the previous event. Then that was one of the requirements to be modeled in as an exponential distributions. Normal distributions, one of the famous one, we always see this one, the bell shape. It is known as most widely used continuous distributions. It was modeled using two parameters, which is uh, this one, the mu, or the mean, or the center. Yeah, that we're showing here. And then the value of the sigma, right, determines the spread. Okay, this one. How large is it going to spread? Okay. So with this, the random variables of normal distributions normally um, it's useful to model variations that caused by many small independent factors. Okay, so for examples like loading time, measurement error, production variation, task completion times, normally that would be normal distributions. But if you have like a normal distributions that only produce positive value, then then you can have like a truncated normal distributions. Okay. And then Weibull is actually a general form of a normal distributions where when you have the more parameters so-called beta and alpha, it will move like a more dynamic way. Like normal is always fit in the center, but with the value of beta, you can somehow reshape those normal distributions into some other shapes like this one. It is very, very variative, but yet it's useful because um, it can give you the chance to model several other um, random events, continuous random events that might have different characteristics, many different characteristics. So it was model has three parameter, so-called the location parameter, which is this one, the scale parameter, which is this one, and the shape parameter, which is this one. Okay, and these often to be used to model failure rates. Okay, failure rates in the reliability. Then we have similar to Weible's log normal distributions. Okay, the distribution is used to simulates a positive value that's skewed to the right. Okay, this would be like the application would be looks like suitable for repair time, delivery time, process time. That will be log normal. And then next, other than that, we do have Poisson distributions here earlier. Then we also need to have the understanding about Poisson process. Okay, Poisson process, which later modeled using Poisson distributions, is a process of counting that represents the number of events occurring over time. Okay, so this is some things that is often denoted as NT, is the counting functions that represents the number of events occur in the interval of time 0 until t. Okay. Mm, why this is important? Because many of the simulations were involving uh, understanding about the countings of some variables in period of time. Okay. Uh, yeah, take example of this. Inter-arrival times is actually a Poisson process where you are actually counting how many times a customer arrive, yeah, arrival 1, arrival 2, arrival 3, from time 0 until time t, for example. Um, next. So in this case, I think the applications of this would be not so yeah, well, I mean, like we are not going to dig deep in the applications of Poisson process, but instead later you can see that some explanations of queuing models would utilize this terminology. Okay, because understanding the meaning of this terminology will help you to understand the next materials of like Poisson process, non-stationary Poisson process, and stuff. Okay. Finally, I would like to jump to this one, empirical distributions. Okay, if your data somehow not fit with uh, any of the distributions that you have that being discussed earlier, what should you do? You can actually create your own formula for the uh, uh, or even you can directly use the observed sample data. Okay, this is so-called empirical distribution. You use because in theory, your data may not follow the distributions like normal, exponential, Poisson. Then you can use it. Use the empirical distributions or use the directly the observed data. Okay. So in summary, this is the end of the discussion of statistical models. So you have been learning about that simulations basically deals with probabilistic system. Real world may contains of many random event. Therefore, simulations model need to address which appropriate statistical distributions could be used. Okay, so what? So therefore, we are reviewing several important probability distributions. We do have discrete, we have continuous, and several variations of it in the discrete and continuous. Okay. Yeah. So now, what is the important task that you need to understand in simulation modeling? First, of course, the collections of the data, input data, and then hypothesis which distribution form would be suitable for the input data. Therefore, after that, you can check how fit the distributions that you choose with the input data that you have. Okay. So with that, you can then later move on to do the simulations. Okay, so I think that would be some things that we left out in the previous meeting. In the next meeting, we will discuss several theory on queuing system. Okay, so if we are doing experiments on queuing system, there is actually theory that you can rely on. For example, if a single server queue, if you create a simulations with a single server queue, even before you create the simulation, if you know the input data, you can directly calculate what would be the expected queuing length, expected what queuing length, server utilizations, because queuing theory has been studied for quite some times. Then there are several proof that in a basic queue model, your model would follow those theory. Okay. So up until here, is there any questions? Have you done the quiz, everyone?
Yes, no, I'm done.
Okay. Okay. If you done the quiz, expect to have next quiz by today, no, maybe tomorrow. Okay. So by that, maybe please check also the our LMS regularly. Okay, so yeah, with this, thank you very much for joining our session today. Hopefully, it still be manageable to like catch up with the materials. But if you have some problems, please let me know. Okay, thank you very much. Good evening, everyone. Bye bye.